This is load switch design. We'll start out with simple load switches that turn loads on and off by connecting them to a voltage source. Controls provided by microcontroller's GPIO ports. Requirements for this iteration of the switch are 5-volt input and 1 amp output. The MCU's GPIO is at 3.3 volts. The loads are purely resistive, and the switches we start with are ideal. In application, load switching is commonly used for power management, as well as protection and fault isolation. So we start modeling the load switch by turning the requirements into circuit elements. So our 5-volt input becomes a DC voltage source. The 1 amp output becomes a 5 ohm resistor. And the 3.3 volt microcontroller GPIO is modeled with a pulse voltage source. And then the transistor is modeled as an ideal voltage controlled switch. Um, we start with the fully ideal switch model. And in this kind of model, the voltage between the positive and negative control terminals will turn the switch on and off. Here's some useful SPICE commands to define the switch, to define the pulse control voltage that models the microcontroller's GPIO output, and some simulation commands. The operating point is one of them, and then the transient analysis is the other one. Um, so to run the quick sim, we need to define the switch, and you can do that with 4 parameters: the on resistance, the off resistance, and the threshold voltage. The last parameter, VH, when this one's set to a negative value, that causes the switch to smoothly transition between the R on and R off values as the threshold is crossed. So here's the result of the transient sim. It's showing the output voltage, and you can see that the output goes to 5 volts right when the control voltage reaches 2 volts and then turns back off as it crosses the same point. Real transistors don't have separate positive and negative terminals for control, so we have to adjust our ideal switch model to more closely represent a MOSFET. We'll also look at what kind of MOSFET should be used for this load switch. Um, so if we start with an N-channel MOSFET, this one can be modeled with an ideal switch by connecting the negative control terminal to the output of the switch or source of the FET. But you can see there's a problem already. If you put 3.3 volts at the gate and the threshold voltage is 2 volts, the switch will only allow 1.3 volts to pass because the control voltage has to be the voltage between the gate and source of the FET. Anything over 1.3 volts will cause the voltage between the gate and source to be below 2 volts, so the switch will turn off. So it stabilizes at a 1.3 volt output. So in order to use an N-channel switch, we'd have to bring the gate voltage at least 2 volts over the input voltage. So you'd need 7 volts at the gate. So for now, this means the N-channel MOSFET, it's not the right choice for this design. So let's look at a P-channel MOSFET. To turn the ideal switch model into a model of a P-channel MOSFET, you connect the positive control terminal to the input of the switch or the source of the FET. If you have 3.3 volts on the gate, the switch remains open. This is because the voltage between the positive and negative control terminals is the input voltage minus the enable voltage. That's 5 minus 3.3 or 1.7 volts. And that's below the 2-volt threshold that we use to define the switch. So let's try bringing the enable voltage down to 0. With the enable voltage at 0, the source to gate voltage will be 5 volts, and so the switch will turn on. Um, this means the P-channel MOSFET can be turned on and off without needing a voltage higher than the input, so it's a good choice for this kind of switch. It looks like we could actually drive the gate directly with a microcontroller output, but there are some disadvantages to doing that. One is that the enable polarity is flipped, so a low output from the microcontroller causes the switch to be on, high output causes the switch to be off. If you want this, that's fine, but in general, it makes for more confusing logic as designs grow in complexity. Sometimes it can also cause issues at startup. Direct microcontroller driving is not flexible. If the input voltage increased, we'd no longer be able to turn the switch off, as the voltage between the positive and negative control terminals will exceed the threshold of the switch. And in reality, input voltages can vary quite a bit. For example, if you're using a lithium-ion battery cell, as it charges and discharges, the voltage can vary from around 4.2 to 2.5 volts. And then other times you might have multiple input voltages that are diode ORed into a single load switch. So you want to be able to handle this case as well. In a real MOSFET, the gate threshold voltage can vary pretty significantly. Even the initial tolerance can vary. It can vary over temperature. It can vary with aging or with other effects like radiation. Another issue is that the on-state resistance, or RDS(on) of the MOSFET, can be high without a decent amount of overdrive from source to gate. And then the speed that the MOSFET turns on and off at is also important, and you can't easily control that with a direct microcontroller gate drive. So we can fix all of these issues by adding another switch, um, and this switch will perform polarity inversion and level shifting. We also need to add a pull-up resistor, which is R2 here. And when the new control switch is off, the pull-up resistor ensures that the load switch stays off as well. So switches, when off, don't have infinite resistance. The equivalent resistance is usually provided in the data sheet. They don't give it to you directly, but it's usually listed as leakage current under a specific voltage bias condition. You can use Ohm's law to get the off-state resistance from the source to drain leakage current. Here, let's say the equivalent off resistance of the switch is in the tens of mega ohms range. So when off, you can look at the circuit as a voltage divider to find voltage across R2, which is the FET source to gate voltage. In this case, it's only 50 millivolts, so the load switch stays off. In the on state, the control switch will also have a resistance or drop some voltage across it. For our near ideal case, we're just using 1 micro ohm, which is a very, very low, unrealistic resistance. But you can try to select a more realistic value if you want. You can use something like 100 milliohms. Running the same voltage divider calculation will show that source to gate voltage exceeds the threshold of the switch, and the load switch can turn on. So we've reversed the polarity. Off from the microcontroller pin results in the load switch being off, and on from the microcontroller pin will turn the load switch on. We're also using the 5 volt from the input to turn the load switch on. This does add a little bit of inefficiency. There's 50 microamps flowing through R2, and that's not going to the load. It's not much since R2 is a weak pull-up. In general, you balance R2 resistance between minimizing the source to gate voltage bias current and ensuring that it's much smaller than the off-state resistance of the control switch.